In our discussion for the general state-space average model, it is defined as an extension of the state-space averaging model that we see previously, where the SSA or the state-space average model talks about only one switching cycle. That means when the switch is closed. And for the generalized state space is an expansion of this state space averaging model that allows more general representation of the DC to DC buck converter, including the non-idealities of the converter and the control method, the feedback, and other dynamic component, meaning that the component or the signal that is changing in the circuit itself. And how about the state variables? So we know that in our previous state space averaging model, we have the Vout and the inductor current as our state space vector. So we can say in the generalized state space averaging model, we can say the state variables are, we have one which is same as the SSA, we have the inductor current, and two, we have the output voltage same as the SSA, and we now introduce a third state variable which is the control input. And we know that the control input of a DC to DC buck converter is nothing but the duty cycle, and it is denoted as the D. So because the control input is the duty cycle, therefore we can say the state variable X is now equivalent to the V0, IL, and the control variable D. So we are talking about some dynamic component and having a control method such as the control input, which is denoted by the D in this equation. Now, since it is just an extension, we can see which of this component is an extension to our previous SSA or the state space averaging model. So we have X dot T in a time domain is equivalent to A average, and we have the XT. Now we had with the B average, we have U of T, which is the input signal. Now we have the BD and the D of T. So this component is our extension where it is a control method known as the control input. And we can say where the A average and the B average and the BD, they are now regarded as the system matrix. So we have a system matrices that accounts for average system dynamics, and we can say this duty cycle is an explicit input to the system that can modulate the converter's operation. We can just substitute the value previously we discussed, and we can now add the control input, which is the duty cycle. So I believe you know what is a duty cycle. Is a pulse train which the width of the signal can be varied to act as a control to most of the DC to DC converters, and one of these converters is the buck converters. So we can provide a summary for the two state, which is the state space average model and the generalized state space average model. And we can say in summary of these two of our model, we have the state space average model. We have XT is equals to A average xt, which is the state variables, plus we have b average and ut, which is the input, and we have the generalized state space averaging model where we have the xt is now equals to a average xt, which is the state variables, plus b average ut as an input plus bd times the dt. And we all know that the matrix A average is equivalent minus 1 on RC and 1 on C, and we have minus 1 on L, and we have 0, and for the B we have 0 and 1 on L. And since we have this 1 on L, therefore in a state space averaging model we are only looking at a one switching cycle where S is equals to 1. So we can substitute this equation to generate a state space averaging model and the generalized state space averaging model. And both of these models, we can say they are a powerful tool for understanding the dynamic behavior of the buck converter under the continuous conduction mode, and also allows for simplification of the system dynamics that are useful for, let's say, one is to do with the control design, and two, we have the analysis, and three, we have the simulation. Why do we mean by the SSA and GSSA? They are the powerful tools because to understand the dynamic behavior in which the state variable, which is the V naught, and the IL, they are mostly changing under a continuous conduction mode. And it also allows for simplification in terms of the system dynamics. So in that case, it is more useful when you want to design a control for the system, and it helps us to analyze the circuit correctly and perform simulation to understand how a DC to DC buck converter operates. And without this prior knowledge, it will be quite difficult for you to analyze a circuit. You can mostly connect a buck converter and apply some input voltage, and you will only see the output voltage, and we know that this will be high and this will be low. So in that case, we are mostly observing the results, and we have no knowledge about the analysis of the circuit, where in our discussion from the beginning we see how we can generate the equation for the system such that we will need to select the resistor and the capacitor and the inductor values. So those components, they have what is called the values, and if we want to produce or design a buck converter to behave in a specific range of input voltage and the output voltage, we will carefully select all these values so that the buck converter will be operating in a specific range. If we say the input can allow for a voltage range between 5 volts to, let's say, 1000 volts. Now from there we will be able to understand in what limit this output voltage will produce. Now this becomes very important when we talk about the analysis, but without this prior knowledge we are going to just observe. We will just connect and see how the output will behave. And finally we will discuss how to derive the transfer function of a DC to DC buck converter, and this will be our final discussion about the buck converter and how we derive a second component all the way to the equation. To derive the transfer function, we are now going to convert the state space model into the transfer function. Our generalized equation we have discussed previously, which is the unified differential equation. We know that we have dv naught on dt, which is equals to minus v naught on rc plus il over c plus 0 vi, and we have dil on dt, which is equivalent to minus v naught on L plus 0 IL plus S over L VI, and this S represent our switch, and it can be 0 or 1. It will have the state 0 or the 1, and we can now simply draw a diagram such that we have the Vref, which acts as an input to our comparator, and we have the controller, and we have the G of S, which will now be our transfer function, and we have the V naught, and we have the switch that is in between, and we have the feedback, which is minus, and we have the plus. Our transfer function will now becomes the output of the system over the input of the system, and we all know that the output of the system is known as the V naught, and the input is nothing but the switch. So we are now deriving the transfer function of this particular model, and we have the input, which is the switch signal, and the output, which is the V naught. And now we have GPS, which can be regarded as our plant model, where we have the control, which is the switch, and because this plant is nothing but a buck converter, so a controller is responsible for providing a PWM signal, and this PWM signal will now act as a switch to the buck converter, and it is connected to the MOSFET. So the signal S represents the PWM signal, and this PWM signal will switch on or switch off the MOSFET in the plant, which is the buck converter. And we can say that the equation now becomes C Si minus A B plus the D, and all this equation can be derived from our state space model. Now the open loop transfer function will now becomes G of S is equals to 1 and 0, and we have S plus 1 over RC and minus 1 on C, and we have 1 on L, and we have the S, and 0, and we have VI on L plus 0, and this should be minus 1, where all of this is derived from this equation, and this and this. Now we can be able to, since we have the inverted here, we have g of s is equals to 0, 1. Now we have s 1 on c minus 1 on l and s plus 1 on rc, and it is now divisible by s plus 1 on rc, s plus 1 on lc, and now multiply by 0 vi over l, where vi is nothing but the input. Now we can have g of s is equals to vi on l over s squared plus 1 on rc s plus 1 on lc. So this now becomes our open loop transfer function of this DC to DC buck converter. Now we determine the closed loop transfer function, and it is quite simple. So our closed loop transfer function will now becomes, from the second diagram, we can now be able to see that we have the g of s, which is our open loop transfer function, and we now have the feedback where we have the voltage ref and we have the v naught, and this is our feedback. So we can now be able to know that our output will be v naught over the voltage ref, which can be equivalent to, like we have said, c of s, which is equals to the output over the desired input, will now be simple as g of s over 1 plus g of s, because since it is a unity feedback, the feedback is equals to 1. Therefore we can say that c of s is equals to g of s over 1 plus the g of s. So this now is our closed loop transfer function. So I believe you can be able to derive the transfer function from the state space model. So in this video series, I believe we have covered most of the things that you need to understand about a DC to DC buck converter in terms of the circuit component, the circuit diagram, the circuit equation, state space average model, and the generalized state space model, and the transfer function that we have discussed here. And in this type of equation, we know that the circuit component is very important. So by analyzing the circuit, we can be able to select the right circuit component for our DC to DC buck converter. Thank you for watching our video. Kindly subscribe to our channel and share this video with your friends so they can also be able to learn